now we come to a beautiful theorem of Bolzano and Weierstrass, which tells us that if you have a bounded sequence, it does not matter what kind of bounded sequence, how the terms are defined or anything, it will have a convergent subsequence. So, this is the Bolzano-Weierstrass theorem. Every bounded sequence has a convergent subsequence. In a sense, we are saying that there is very little space between two numbers. If you have infinitely many terms squeezed in between two numbers, then there has to be some point where a subsequence will converge. So, the idea behind the proof is idea of called divide and rule. So you start with an interval, and let us say it's we have L, it's our lower bound, M is our upper bound, and we have this sequence. It's got a bunch of points. So there's A1, A2, A3. I don't know how they are arranged. A4. They are somehow arranged inside this interval. So what we do in the proof of the Bolzano-Weierstrass theorem is, first we start with this whole interval, and then we divide it exactly into two halves. Now, out of these two halves, there are infinitely many terms of the sequence, remember, and so if both halves contain only finitely many terms of the sequence, well, that is not possible, right, because there is A1, A2, A3, there are infinitely many terms of the sequence. So, infinitely many of them have to either lie in the left half or in the right half. Okay, so let us say in this case it looks like maybe there are more in the left half. Let us assume that there are infinitely many elements in the left half. So, then we will forget about the right half and we will focus our attention on the left half. So, I will just focus my attention on this, and now I will take this half interval and again divide it into two equal parts. And the same thing happens again, infinitely many terms will either lie in its left half or right half. Now, this time let us say that there are infinitely many terms in the right half. So, we will forget about the earlier interval and look at only the right half of it. And you continue in this way, you keep reducing the size of your interval and cutting it smaller and smaller, but making sure that each smaller and smaller interval has infinitely many terms of your sequence. And then once you have done that, you can start constructing your subsequence. Your first term of your subsequence can just be A1, then A2 will be a term in one of the half intervals, sorry, not A2 but B2 rather, the subsequence term will be in the half interval, the next will be in a smaller interval and so on. I will explain the details as we go along, and you will be able to generate a convergent subsequence. So, let us try to write down this idea precisely. So, let A n be a bounded sequence. So, what that means is L is less than or equal to A n is less than or equal to M for all n. Okay, so I am going to now construct a sequence of intervals. So, let us say x1 is my, so I am going to construct two sequences x1, x2, x3, y1, y2, y3. x1 will be the left ends of the intervals I will construct, y-ends will be the right ends of the interval I will construct. So, the process of this proof itself is an inductive process. I will do a construction which will be inductive. So, x1 I will take to be L, it is an algorithm in fact, and I will take y1 to be M, and I will take z1 to be L plus M divided by 2. So, the midpoint of x1 and y1. So, let us just go back to this picture over here, and what I have at this stage is this here is my x1, this here is my y1, and z1 is somewhere right in the middle. So, now you look at the set S equal to n in n such that x1 is less than or equal to a n is less than or equal to z, and T to be the set n in n such that z, well, this is z1 is less than or equal to a n is less than or equal to y1. Okay, so these are subsets of the set of natural numbers, and of course, if you have any natural number, then a n lies between L and M. So, it lies between x1 and y1. So, S union T is certainly the set of natural numbers, which is an infinite set. Now, the union of two finite sets is always finite. So, one of these sets has to be infinite, right. So, if S is infinite, take x2 to be equal to x1 and y2 to be equal to z1, which means now out of this interval I have chosen the left half. So, this is x1, this becomes x2 and this becomes y2. The other option would be that T is infinite. It is of course possible that both are infinite, but just I will first look at S. If that is infinite, I will do this. If S is not infinite, then T must be infinite. In which case you take x2 to be z1 and y2 to be y1. So, now what I have done is I have chosen my x2 to be here and y2 to be here. I have chosen the right subinterval. And now what do I have? We have n belongs to n such that a n lies between x2 and y2. This is an infinite set. Now, what we do is we repeat this process. So, suppose we have worked this up to the ith stage. So, suppose we have constructed xi less than yi such that the set of n such that a n lies between xi and yi you define zi to be the midpoint of xi and yi. So, zi is xi plus yi by 2, and now you look at the set S consists of those indices n such that xi less than or equal to a n less than or equal to zi, and T to be the set of natural numbers n in n such that zi is less than or equal to a n is less than or equal to yi. And again the union of these two sets is infinite. So, if S is not infinite, that is if S is finite, then T will have to be infinite. So, again what we do is if S is infinite, choose xi plus 1 to be xi and yi plus 1 to be zi. So, I am choosing the left half of the interval xi yi. Otherwise, we must have T is infinite, and so you choose xi plus 1 to be zi, whereas yi plus 1 to be yi. So, what have we done by this iterative process? So, we started with x1 equals L, y1 equals m, and then we have divided into 2 and chosen one side which has infinitely many parts, and that is the interval x2 infinitely many terms of the sequence, and that is x2 comma y2, and then we have x3 comma y3. So, if you think about it a bit, you will see that our construction has the following properties. So, what have we constructed? We have constructed sequences xn and yn such that, well, firstly the sequence xn. So, notice always xi plus 1 is either xi or xi plus 1 is zi. So, xi plus 1 is always greater than or equal to xi for all I in n. And secondly, yi plus 1 is less than or equal to yi for all I in n, just because yi plus 1 is either zi or it is yi. And the third property is that the difference between xi and yi, so that is always yi is great to the right of xi, and so what we have is yi minus xi, and this difference is always, to start with it was L minus m, then it became L minus m by 2, and so this is always L minus m, or maybe I should say m minus L, because m is larger, m minus L divided by 2 to the power, well, let us see, when I is equal to 1 it is exactly m minus L. So, I should probably write I minus 1 over here. Okay, so we have these three properties, and let us see if we can somehow use these to find a limit for a subsequence. So, firstly, what would that limit be? See, we have here an increasing sequence, all the terms are bounded above by m, the sequence xn. The sequence yn is a decreasing sequence and all the terms are bounded below by L. So, what we know is that both these sequences converge and have to a limit. And this third property tells us that these two sequences are very close together, and that will mean that they have the same limit, and that limit will be the limit of the subsequence that we choose. So, let us do that. Let L be equal to limit as n tends to infinity xn, and let us say m is limit n tends to infinity of yn. We know that these limits exist because these are bounded monotone sequences, and now what we know is that I claim that L is equal to m in fact. So, let us look at m minus L is equal to limit as n tends to infinity yn minus xn, but we have shown that yn minus xn is m minus L divided by 2 to the power n minus 1, and this is 0. So, what we have is L and m are the same. So, this L is going to be the limit of the subsequence that we are going to construct. So, now we come to the last step of the proof of the Bolzano-Weierstrass theorem, which is the construction of the subsequence. So, we want to construct a subsequence Bk equals Ank. So, we basically want to construct set n1, n2, n3. So, n1 less than n2 less than n3 and so on. So, first you can just take n1 to be equal to 1. So, and so what is it? B1 is equal to A1. Now, what we know is that this B1 lies between x1 and y1, just because every term in the original sequence was lying between L and m, x1 is L, y1 is m. Okay, so now how do we choose the next term? Now look at x2 comma y2. So, there are infinitely many terms of the sequence which lie between x2 and y2. Take the first term after a1 that lies between x2 and y2. So, let n2 be the smallest natural number n such that n2 is greater than n1 and x2 less than or equal to n is less than or equal to y 2. This has to exist because infinitely many terms of the sequence lie between x 2 and y 2. In this manner, you having chosen n 1, n 2 up to n k, you choose n k plus 1 as follows. So, having chosen n 1, n k, choose n k plus 1 to be the smallest integer n such that n k plus 1 is greater than n k. This is a condition that we definitely need for a subsequence, and x k is less than or equal to a n k plus 1, x k plus 1 is less than or equal to a n k plus 1 is less than or equal to y k plus 1. So, this is our subsequence. So, we have B2 is a n 2, B3 is a n 3, and so on. Now, the way we have chosen our sequence, we have Bk lies between xk and yk. And so, by the squeeze theorem, limit k tends to infinity, Bk lies between the limit as k tends to infinity yk and limit as k tends to infinity xk, but both these are equal to L. So, limit as k tends to infinity Bk is equal to L. This concludes the proof of the Bolzano-Weierstrass theorem, because what we have done is we started with the sequence a n, and then using this divide and conquer and this recursive strategy, we were able to construct a subsequence that converges to a definite limit L. Now, we are ready to show that every Cauchy sequence is convergent. What is the idea behind the proof? Well, from what went on before, we have already seen that a Cauchy sequence is bounded, right, and then we have seen that a bounded sequence has a convergent subsequence. So, this Cauchy sequence will have a subsequence that converges to a certain limit, and that means we found the limit that we want. We will just show that the original Cauchy sequence must converge to that same limit. So, let us write down the proof. So, let a n be a Cauchy sequence. Since a Cauchy sequence is bounded, the Bolzano-Weierstrass theorem implies that it has a convergent subsequence. So, while making such bold claims in a proof, it is good to explain why this is true. So, it is true because firstly, Cauchy sequences are bounded and bounded sequences admit convergent subsequences. So, let us say limit k tends to infinity of a n k is equal to L. Now, I want to show that a n itself converges to L. So, claim is that limit n tends to infinity a n is equal to L. So, I want to show that as usual we will do some rough work over here. I want to show that a n minus L is less than epsilon. But what I know is that a n k minus L is small. So, I will just try to make a n k minus L less than epsilon by 2, a n minus a n k small, and then what we know is that this would happen because it is a Cauchy sequence, and from this I would be able to show that a n minus L is less than epsilon So, let us try to write this down properly. Choose n1 such that for all k greater than n1, a n k minus L is less than epsilon by 2. And then you choose n such that for all m n greater than n, a m minus a n is less than epsilon by 2. Now, I want to bound a n minus L. So, now suppose n is greater than n, little n is greater than capital N, then I can find k such that n k is greater than n 1. Why is that? Well, this sequence n 1, n 2, n 3, it is an increasing sequence of natural numbers. So, in fact, n subscript n 1 itself will be greater than or equal to n 1, n subscript n 1 plus 1 will be strictly greater than n 1. So, then what we have is that a n minus L is a n minus a n k plus a n k minus L, which by the triangle inequality is less than or equal to a n minus a n k plus a n k minus L. And now, this first term is less than epsilon by 2 because a n is a Cauchy sequence, and the second is because the subsequence goes to the limit L. And so, we have shown that the original Cauchy sequence itself converges to the limit L.